Good afternoon, ladies and gentlemen. Welcome to TechGig webinar series, our endeavor to impart techies. We believe that sharing of knowledge is the key to enhance our skills and to assist professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is delivering business value with big data. Our guest speaker today is Stephen Lofthouse, SAP Program Manager and Course Leader, MSc Big Data Analytics at Sheffield Hallam University. Steve is the course leader for the MSc in Big Data Analytics at Sheffield Hallam University. He is the lead of the university's SAP program and teaches SAP at both undergraduate and postgraduate levels. He joined Sheffield Hallam in September 2010 after working in pharmacy within the National Health Service for 13 years. Steve's research is in the field of big data, and it's used by law enforcement agencies in the fight against organized crime and terrorism. And he is currently involved in a number of projects in this area. Steve is a fellow of the Higher Education Academy, registered with the General Pharmaceutical Council, a SAP Mentor, and leading light within the SAP University Alliance, an organization of which Sheffield Hallam University was a founding member in the UK. So without further delay, I introduce you all to our guest speaker. Over to you, Steve.
Good afternoon, ladies and gentlemen. Thank you for the kind introduction. Kind and comprehensive introduction. Thank you very much. Okay, so what's the plan for this afternoon? As has been nicely kind of introduced, I manage the SAP program here at Sheffield Hallam University. I lead our course in Big Data Analytics. I do a lot of work with SAP. I research within security. And as you can see at the bottom of the screen, my email address is there. If anybody'd like to get in touch, by all means do so. The schedule for this this session, I want to talk about a project that the university is involved with, and then we'll walk through some of the techniques that we've used, and we'll have a look at some of the results of those techniques, and then I'll explain the wider kind of implications and how you can apply the same kind of techniques and the same kind of ideas to your own kind of commercial sphere. Okay, then let's dive in. Okay, so the university is involved with a project with South Yorkshire Fire Service. South Yorkshire Fire Service have 13 years worth of data related to the kind of fire incidents that they get called out to. So they've asked the university to look at that data and examine that data with the kind of three aims. One, we want to understand the risk of fire across the city where the university is based, across Sheffield. We want to use that risk model to be able to create a predictive risk model. So we want to be able to take the risk model that we create, the map that we create, which says, you know, there is a high chance of fire in this area, there's a low chance of fire in that area, and we want to start and merge that with real-time data. So maybe we're pulling in weather feeds, maybe we're pulling in traffic data and Twitter data, so that we can start and predict the risk of fire, the risk of car accidents in real time. And then we want to use this data to better understand the processes which happen within the fire service. So what happens when somebody rings the fire service and logs an emergency and requests help? So we want to better understand what happens there, with a view to maybe changing the way that the service is delivered, maybe changing the way that we train staff, maybe identifying patterns. And it's this understanding and optimizing of internal processes, which I'm going to focus on in this particular session, because I believe that has the kind of greatest applicability to the diverse worlds in which you guys come from. Okay, so the software that we've used is a piece of software called Traminar. It's mainly used in the world of biology for looking at gene sequences and identifying patterns and relationships and correlations within gene sequences. And you'll see why that's been quite useful for us to use, and why it's been quite insightful for us to use as we go on. But you can get hold of a copy of that software using the link which is on the slide. The software is open source, so on the one hand it is free to use, free to download, but the other side of the coin, it comes with no guarantees, and there are no kind of real instructions for use. It is a matter of diving through textbooks and diving into academic papers. But having said that, the language that the software uses is R, which is a mainstream kind of mathematical programming language. So it's quite, there are lots of texts widely available for people to kind of get hold of and embrace it. Okay, so the data that we got hold of from the fire service, we're kind of working incrementally. So we started off with 1 month's data, which was 2,600 records. And you can see a sample of the kind of data we were looking at on the screen. Now this data is generated by an operator. So a member of the public would phone the fire brigade, phone the emergency services, and log an emergency. And as the member of the public is giving the operator that information, the operator is filling in kind of prerequisite text boxes on the screen, drop-down text boxes. These responses are pre-formatted. They are not free text. So this is one set of data which we got hold of. There are 2 other sets of data which we have yet to look at. One of the other sets of data is machine-generated GPS pings. All of the fire engines have a GPS transponder in them, and that sends out GPS coordinates every 10 seconds, so you can plot and locate fire engines. We've not looked at that data yet. And the other set of data is free text data. So when the fire crew come back from an incident, they write out a report, and that report is free text, so we could mine that data. And that is something that we will look to do in the future. But at the minute, we have 13 years worth of kind of incident data, operator-generated data. And just to give you a rough idea, 1 month, so we took October 2013, that's 2,600 records. Which might not seem a lot for a month, but when you scale that up to 13 years, you're looking at a large amount of data to kind of trawl through. The data itself, it looks like this. You've got an ID for the incident, and then you've got various kind of pre-formatted text codes which define what happened. For example, ink create, the incident was created, ink status, the status was changed, and so on and so on. Some of the entries end with close, in which case the entry was just closed, the incident was just closed, nothing happened, and some of the entries end with an appliance being dispatched. So we took this data and we started to run some kind of sequence analysis on it. Okay, so the sequence analysis that we were doing, we want to look for similarities. Sequence analysis is about a study of similarities. So we're looking for similarities in those incidents. We're trying to identify the features of those incidents, and we're trying to identify the differences of those incidents. And how that applies to you in a commercial world, we'll kind of come on to a little later. So we were trying to find sequences, we were trying to find features, we were trying to find differences. Okay, so the software we were using to do that was the software package called R. So if I just come out of this presentation and drop into R. Now, as I said, this software is freely available. It's open source. You can download it yourselves. Excuse me. Sorry about that. You can download it yourselves. And having downloaded the R environment, you would then download the TrayMineR package, which would enable you to do the sequence analysis. Now, what I'm going to do here is I'm going to run through the code that we've used to do the sequence analysis. And at a certain point, I am going to stop and switch back to PowerPoint slides. The reason for doing that is quite simple, that if I ran the entire analysis, it would take far too long, much longer than we've got to do this presentation. So, first of all, I need to kind of tell the software that I want to use the TrainMiner library. So, I give it the command library TrainMiner, and R is case sensitive. So if you're having problems, it may be that the case is incorrect. So we want to use the functionality of the TrainMiner, and I want to tell the software that actually this is the package that I need to use. So I want to require that software. Now that I've got an extraction of the data, I've got that out of the database of the fire service, and I've got that saved as a CSV file on my desktop. So now I need to read in that CSV file and store that CSV file within the environment so that we can use that. Okay. Okay. So what this command is doing, I've got an object variable, syfr, into which I want to load the data, and then I'm telling the R software, the R package, that I need to read the table from this file, the syfr test.txt, and that is a CSV file. It's formatted CSV. The header is true, so there is a header within that file which identifies what the column names. I then define how the data is separated. In this case, it's separated by space, what an empty string looks like, and I want to fill all of the columns. So I say that I set that value to true. Okay. So having loaded the data in, I can summarize it, and just to have a quick look, just to be sure that the data has loaded into the R environment, and we can see there that the data has come in. How do I know that it's come in? Because I'm being shown this blue text. If the data hadn't got in, I would obviously be shown an error message. Okay, so now that we've got the data into the R environment, we need to now create a sequence object. Remember, we're looking at the sequences of this data. I want to look at the similarities, the dissimilarities of this data. So I need to create a sequence object, and that sequence object is what the TrainMiner package will use to perform all of the analysis against. So I can do that quite simply just by dropping in the sequence definition command. Okay, so what we're doing here is that we're saying I want a sequence definition, and I want you to store the sequence definition in this object called syfr.seq. The data that you're going to use is syfr, which is this object here where we've loaded the data in from this CSV file, and the variable is null. So that tells R that it should utilize all of the columns within this data set when it's creating this sequence object. There are other values that I could put in this command, values to tell the package what it's going to do with missing values, what it's going to do with color schemes and things like that, but I don't need to do that. I'm quite happy that we've got in the information that we need. Okay. Now, for myself, for this data, we're interested in the similarity of various entities. How similar is one of those entries, one of those fire incidents, to another? Because ultimately, I want to be able to group those entries based on their similarity. Now, what I need to do in order to compare the similarity, in order to group them, is I need to calculate the distance, the dissimilarity, calculate the dissimilarity of one of those entries to another. Okay, so I need to calculate how similar each of those incidents are to each other to enable me to then group those entries based on their similarity. Okay. Now the way that we do that is we use there's a method in Trainminer called sequence distance, secdis, and we use that command to calculate this similarity. So if I pop that in, okay. So this is going to, or not in the case of me, but that will calculate the similarity between those entries within that text file. And based on that, we're able to then kind of calculate the distance, how similar they are to each other. Okay, so then we can start and say, actually, calculate the distance between them. And produce me a matrix. I'm getting some errors in my text file, but that's not a problem for what I'm trying to achieve. So calculate the distance within that text file, calculate how similar those entries are to each other, and map that. And having mapped that, then what we could do is we could go on and we could then graph those results and produce a dendrograph that would show us how similar those entries are to each other, and kind of place them in families. So if I just show you the code for doing that. Now I've commented this code out, and there's a reason for doing that, not least because my text file seems to be producing errors, which is slightly puzzling. But if I ran this particular piece of code, it would produce a very nice dendrogram, which we'll see in a moment. But if I did run that piece of code, it would take time, more time than we've got in order to do the analysis. So we calculate the sequence, we calculate how similar those entries are to each other, and run this particular code to kind of graph those results, and that gives us a very nice graph. It gives us a graph, excuse me, like this one. Now, excuse me. Along the bottom of the screen, these are the types of instance. So this is the data that we were looking at. This is the 250,000 records. This is the data we're looking at, and so these incidents are now mapped along the bottom of this graph. And these indicate how similar these incidents are. These incidents are now ranked by similarity. So all the incidents in this particular area are similar. All the incidents in this particular area are similar. It turns out, when you do this, that there are about 15 types of incident that the fire brigade get called out to. So of those 250,000 incident records, there are actually only 15 types of incident that the fire service get called out to. Now that is quite a useful piece of information, because if you're planning on putting equipment on a fire engine, you now know that for the majority of the things that you get called out for, there's only 15 types of incident. Therefore, you only need to stock equipment on a fire engine to deal with those 15 types of incident. If you ensure that your staff, your firefighters, are trained to deal with those 15 types of incident, then they're going to be able to deal with the majority of the call-outs that they receive. Now we want to expand this and look at the kind of entire data set, because if you do this, it changes the way that the service operates. It turns out, if you look at this particular data, that the majority, the largest type of call that the fire service are called out to is a well-intentioned false alarm. So that's where somebody smelt smoke or something's happened, and with the best of intentions they've phoned the emergency services, and the fire brigade have attended, they've turned up on the scene, and they've decided that there is nothing that they need to do. So you have a well-intentioned false alarm. Is there any need to send a fire engine, a large vehicle staffed with 6 or 7 firefighters, a whole range of equipment that is actually quite a slow-moving thing? Is there any need to dispatch that vehicle if the majority of the calls are well-intentioned false alarms? Could you change the way you deliver the service? Why not dispatch a fast car? Why not, as daft as it may sound, send a fireman in a Ferrari or a Lamborghini or a sports car? They can get to the incident very, very quickly. We've only dispatched 2 members of staff. There isn't as much kit on the vehicle, so it can get through traffic a lot faster. Why not send a motorbike so that the motorbike can get to the incident really, really quickly? And if there is a need to send out a fire crew, to send out more equipment, that motorcycle rider can request that, and there isn't much of a delay in doing so. So by looking at this data, by sequencing this data, we're able to identify patterns, identify kind of sequences and families and similarities, and based upon that, we can change the way that we provide the service. Now, I appreciate that this is a fire service, and it is in the UK, it will be quite a contentious thing to say, do you know what, we're going to start and send motorbike riders out there. So maybe that's something that won't happen. But if we look at a more commercial application, let's look at a more commercial application. Let me kind of imagine a scenario. Let's imagine a situation. You have a supermarket. And the supermarket places an RFID transmitter, an RFID tag, on every one of its shopping trolleys and every one of its shopping baskets. And around the supermarket, in 3 or 4 places along each of the aisles, they place an RFID receiver. Now, all of a sudden, we're in the position of being able to track a customer through our store. So a customer attends the supermarket, takes a shopping trolley, and walks around the store, shopping, picking up goods as they go. And as they drive that trolley, as they carry that basket around the store, the RFID transmitters are picking up as that trolley passes. They can tell whereabouts that trolley is, whereabouts that shopper is within the store, how long they've spent on each particular aisle, how long they've spent on each position within the aisle. If we've got 3 or 4 transmitters down the aisle, we can track where people are within the aisle. Then, having done your shopping, the shopper then goes to the checkout, and the goods are put through the point of sale system, at which point we're able to link the RFID tag that is on the shopping trolley, on the shopping basket. We can then link that to the actual purchasers and the items that the person purchased. So now we have a map. We have a map of how that shopper moved through the store, and we have a map of the products that shopper bought. Now, maybe in your particular supermarket, you use loyalty cards. Loyalty cards are quite a common thing in the UK, where you would scan your loyalty card and claim points, which enable you to get discounts and things like that. But it also enables the supermarkets to tie your purchases to a known identity. So maybe you scan the customer's loyalty card. So now all of a sudden we have a known identity because we've scanned the customer's user card, loyalty card. We have a known identity. We have a purchase. We have items which we put through the point of sale system, and we have a map of whereabouts in the store that shopper went. That data is very, very similar to the data that we've got from the fire service. It's auto-generated data. So we can run that sequence analysis on this kind of mapping data, and if we've got enough of it, if we've got enough shoppers coming through our store, all of a sudden we can start and build up a picture, we can start and build up clusters and identify types of shopper. So maybe we get shoppers, the majority of our shoppers are people who just rush into the store or in an evening after work and grab a few items from the fresh counter and maybe some milk. Maybe a large proportion of our shoppers are female, mothers or wives who are doing a large weekly shop, once a week, purchasing a lot of groceries. Maybe we've got younger people coming in who are just purchasing a few groceries and maybe some alcohol. We can identify different types of shopper. And if we can identify different types of shopper, if we can identify different buying patterns, different shopping patterns that these shoppers have, all of a sudden we can start and structure our shop. We can change the layout of products. Maybe the large portion of our customers come into the shop wanting some fresh food and a bit of milk. Well, then we've got two decisions. We could either say, actually, I'm going to put the fresh food and the milk at the front of the shop where these people can just run in, grab them, pay for them, and go. Or maybe we're a bit more savvy. Maybe we put the fresh food at the front of the shop and the milk at the back of the shop. So now all of a sudden our shoppers run in and grab the fresh food, but then have to go through the entire store, exposing themselves to all our marketing, all our fresh products, all our brand new products, our offers, our tantalizing items, before they get to the milk. So maybe in their passage through our shop, they will be more inclined to buy, to pick up more things. So just by placing these little RFID tags on our shopping trolleys, we can start and track shoppers through our shops. Now, please don't be under any illusion. This is done. This is done in the UK. We don't use our RFID tags in the UK. We use the kind of mobile phones that people carry, and we will put a wireless network in the supermarket and tell shoppers that the wireless network is free. And people will switch on their mobile phones, try to connect the wireless network, and they will connect the wireless network, they can surf the broadband. But because we've put wireless access points throughout the store, we can track people through the store using the MAC address of their mobile phone as a unique identifier. So we're able to get this kind of data, and supermarkets and stores do get this kind of data and will lay out their stores based upon that. So that's an idea of a commercial application for that. So you could arrange your products based upon the shopping patterns of your customers, and you could equip your store, you could train your staff based on the kind of customers that you were coming to your store. Okay, so one of the things that we did, going back to the fire service data, was we ranked the responses. So we got our cluster analysis, and this grouped the analysis into families, and we were able to identify types of incident, and then we ranked those types of incident in terms of which was the most common and which was the least common. And here we've got the top 15. And you can see that really the top 2 incidents don't require any interaction. It's very quick. It's very quickly apparent that these incidents are not needing of the fire service. So the top 2 incidents that come through do not need the fire service. The next one incident, number 3, yes, that does require a fire engine to dispatch. We can see here that the final kind of entry, mobilized rest mobile. So this is an engine, a fire engine has been dispatched. But the next 2 close. So in these 2 incidents, yes, they probably needed the fire service, but when we work our way through it, we do not need to dispatch an engine. We do not need to dispatch an engine. So again, we can see that in terms of the kind of common incidents that we're dealing with, the most common incidents do not require the fire service. And of the kind of top 5 incidents, in only one of those do we have to send an engine. So again, you can staff your fire service, you can staff your fire engines, you can equip things in such a way to account for this kind of insight. The majority of the incidents that come through do not require somebody to mobilize a fire engine. And maybe that's the same with the kind of shoppers that we're dealing with. The majority of the shoppers that come through our store go around our store in this particular sequence, in this particular way. So we need to structure our store in this particular way. They are purchasing these kind of products. There's a degree of commonality around the products that they're creating, that they're purchasing. There is no reason why we cannot perform sequence analysis on users' shopping baskets. Why not perform sequence analysis on users' shopping baskets? Look for kind of common patterns around the kind of products that people buy, and maybe recommend products based on the kind of products that people buy, the clusters of things that people buy. Maybe start and group things together based on the clusters of products that people buy. So you can perform this kind of analysis on shopping baskets as well. Okay, so you could identify typical buying patterns. These families of customer, this type of customer, they typically buy these kind of products. And based on that, I could recommend this kind of product. So you're a customer, you live within family type A that we've identified using this sequence analysis that, that you're a type of customer that lives in this sequence, you buy these kind of products. Well, I noticed that on this particular shopping incident or this particular shopping outing, you've not bought an umbrella, you've not bought some tea, so perhaps I could recommend that for you. Perhaps I could give you a discount voucher for a product that you've not purchased for a while, something like that. But we can identify all that from the sequence analysis. We can identify how people pass through our shop. Is the way that our products are laid out on the shelves the best way? How do people move through the shop? Do they run through it? Do they move quickly? There are areas of the shop that people never venture to. Do the products in that particular area never get sold? Are there areas of the shop that everybody ventures to? Because if there are, maybe that's where we need to be putting our offers. Maybe that's where we get advertisers in. People promoting their products. If we can identify and prove that an area of the shop is most likely to have foot traffic through it, then maybe we could charge our advertisers a bit more to advertise in that particular area or to place their products in that particular area. Maybe we have products that we really want to sell. Maybe they have the highest markup, maybe they have the highest profit. We could put those products in that particular area just from identifying how people pass through our shop. We could start and understand which pattern, which type of shopper, which pattern through our store produces the highest amount of profit, and then we could start and ensure or start and influence people to take that passage through the shop in order to increase the amount of profit that we're generating. So for ourselves, what we did, having done the sequence analysis on the fire service data, and then having identified and ranked these sequences, we went on and looked at the staff. So there are operators at the end of the phone who receive the calls from the members of the public, and these operators are identified on this particular graph, and I've covered up their identities with this kind of black line just to maintain anonymity. This is an ongoing research project, so I have to be careful with these things. So we've got kind of the operators here, and then these row labels down the side. These row labels relate to these particular incidents that we saw here. So the row labels down the side relate to these incident clusters here. And this allows us to see which operator used which cluster and how many times they used that cluster. Now, the reason for doing that, if you are, in our particular case, if you are responding to an incident, there is a set way of responding. The operators are trained that in the event of a car accident, you need to obtain this kind of information, how many vehicles were involved, the location, who's injured, this kind of information. So there is a set procedure that people need to follow. And getting this kind of cluster information, we can see how often the operators are following these sequences. And that has an impact on staff training and how we train the operators. We could maybe look at this data and see that somebody uses a particular cluster far more times. So we can see in this first column, row label number 3, this particular operator uses that particular cluster 76 times. So we can see that this particular cluster, number 3, which results in an engine being deployed, that particular cluster is used by this first operator 76 times. And yet it's used by this sixth operator only once. Now, why is it that it's only used once by this particular operator and 76 times by this particular operator? Is it because this particular operator works at night? Is it because they were a supervisor? Is it because they're not particularly well trained and don't know about that sequence? So if we start and map those sequences of incident response, if we start and map them against the operator, we can start and identify who's using what sequence, how often, and then we can start and dig a bit deeper and decide if people need training. So from your own point of view, from a more commercial point of view, that would allow us to kind of identify which shoppers belonged to which clusters. So if you had loyalty cards and store cards which would enable you to identify your shoppers, a known identity of shoppers, and then you had the various clusters which were maybe the contents of a shopping basket, or maybe you could do the same analysis for the pattern, the way a shopper moves through a shop. All of a sudden you can start and see which shoppers correspond, or which shoppers are affiliated with which particular cluster. And again, that gives you more insight into the kind of person who is using your store, the kind of person who is purchasing from you. So maybe you could identify shoppers by which cluster they're belonging to. Maybe you can gain, or you could gain more insight into their buying habits, into their patterns, and based on that, you could start and generate offers based on a particular buying pattern. So if a shopper is identified and matched with a particular cluster, you could then generate offers which were targeted at that cluster and be far more acceptable to that particular customer. So rather than generating offers which a customer is going to ignore, which are not going to encourage your customer to come back to your store, you're able to generate offers which are far more targeted and far more likely to succeed and bring a shopper back into your store, increase footfall, increase buying, and increase profit. So there's a commercial application for that. Okay, so throughout this presentation we've had a look at sequence analysis. I've spoken about how we've used sequence analysis when we've been analysing data from the fire service, and we intend to go on doing that and expand the breadth of data and the breadth of analysis, and hopefully help the fire service through some of the changes that they want to make. And hopefully I've identified some of the ways that you could use those similar techniques within a more commercial sphere. And I've used the example of a supermarket, of a shopping chain, where you could invest and utilize the benefits of store cards and kind of footfall mapping. So now I shall throw it back to my colleague and ask if anybody has any questions. If anybody would like to ask any questions, I'll try my best to answer them.
Well, thanks, Steve, for the wonderful session. We have questions pouring in from the users. I've started assigning them to you. I hope you can see them.
Yeah. Views for optimizing traffic light timings are there any? How do we consider endogram? How do we decide what level we need to? Once you look at the data for past 13 years, with all columns fields fully populated, with the missing data out, if the data was missing, how do you make sure that it gets populated, or if you've left things around? Okay, SWAYAM. Let's start with SWAYAM because SWAYAM was first in there. Once you took the data for the past 13 years, was all the column and fields fully populated? Were there missing data also? If there was missing data, how do you make sure that the missing data gets populated? And if you list missing values, how did you make the analysis? If we have a quick look at the fire service data, the kind of sample that I was working with, if I just dive into my D drive and pull up a sample of fire service data. Okay, and pull this over here. You can see that these entries are of different lengths. So in some cases, the entries are quite short. You can see here ink status closed, so that incident was closed quite quickly, didn't require an attendance, where in other cases, if you take row 70 for example, the entries are really quite long. So some of the R commands that we were using when we were specifying the kind of null values, we were telling R that it needed to use the whole of these entries. So when we were saying in that kind of sequence definition, if I drop back into the R software, so when we were using this command to create that sequence object, we were saying var equals null. So we were telling R that it needs to account for all the data. The data is of different lengths. The entries are of different lengths, and it should account for the whole of these lengths, regardless of the fact that they're of different lengths. So the short answer is the commands that we used in R account for the fact that the entries are of different lengths. Is there missing data in that sense? No, because the fields have to be populated. They are mandatory fields within the system that the fire service use, so they have to make entries within those fields. The missing data problem will probably come up when we start and look at the free text data, but with all these things, the free text data is going to be the more interesting data. One of the interesting insights that we're already seeing with this data is that you can see an arsonist in generation, really. So an arsonist is somebody who gets a thrill of starting fires, and they can be quite dangerous people. But an arsonist will not just start a house fire. They will start off quite small. So maybe they burn down a litter bin. Maybe they move on and then burn down somebody's shed or something like that. So using kind of sequence analysis, you can start and see kind of arsonists in generation. You can map that to kind of geographical coordinates, and you can see areas where arsonists are growing. And maybe you put in more social kind of resources within there. So hopefully that's kind of answered that. How do we consider that? How do we decide what level we need to consider the dendrogram? I think that comes out in the sequence analysis that you're doing. At what level you're going to consider it. Really, the sequence analysis for us showed that there was about 15 kind of top 15 incidents, and maybe that was an arbitrary number that we picked to kind of work with based on the kind of people that we were working with. Maybe you could have said, you know what, I want to do a dendrograph that will look at the kind of top 25, the top 50. And then I think it's a matter of going back to the business and having a conversation on the business with the business and deciding how useful that kind of detailed information actually is. So for us, there is no point doing a level where you're looking at, say, the top 25 or the top 50, because you cannot equip a fire engine to cope with the top 50 incidents. So for us, maybe it was an arbitrary number, but it was a number based on a conversation with the kind of commissioner, as it were. So I suppose for itself, in a business point of view, it's a conversation with the business. It's a conversation with the people who want the data around what kind of level of detail you want to go down to. If you're looking at it from a commercial point of view, how many families of shopper do you want? How many types of shopper do you want? How many types of shopper do you want to cater for? And that may be a decision you take based on the size of your store. If you were looking at some of the larger hypermarkets, then maybe you can stock more products and therefore cater to a wider variety of customer. If you're dealing with a much smaller kind of premises, then maybe the level of detail that you go into is much smaller. Because at the end of the day, the more, with respect to supermarkets, the more family of shopper that you cater for, the more products you're going to have to stock, and then maybe the more conflicts you're going to have to deal with. If one particular type of shopper explores your shop using one particular route and another type of shopper explores your shop using another particular route, you're going to get conflicts with regards to where you place products and the products that's most popular. So in some ways, it's a business decision as to how much detail you need to go into. Could you use sequence analysis for optimizing traffic light timings? Are there any existing applications? I don't see why not. However, it's not an application that I've come across. So I'm not aware of any applications of it, really. I don't see why not, in the sense that it's used, sequence analysis is used for looking at similarities and dissimilarities, and one would presume that there would be similarities with regards to traffic patterns at different times of the day, and therefore you could base the timings of the traffic lights based on kind of the different times of the day. I know there is research into kind of real-time traffic analysis and adjusting traffic light timings based on real-time data. So possibly that would be an area that to look at more so. How to figure out patterns in data using R? Could you stress more a bit how you figured it out? Lakshmi. The patterns, the Traymine R is a software that we used to identify patterns. So in that sense, we didn't have to identify patterns. The Traymine R software identified them for us. And I appreciate that I had one or two problems with the code, which was working fine yesterday, rather frustratingly. But the Traymine R software, it identifies the patterns so that you don't have to. So it's the software itself which is producing this dendrogram, which is calculating the similarity within these particular patterns. The software does that for you, so you don't have to. It's the software that is ranking those patterns based on their occurrence and their popularity. So again, you don't have to. The software does it for you. So what, Swayam, what's the difference between model and predictive model? In terms of fire risk, the model is static, and the predictive model would be dynamic. So if you imagine, for example, a map of New Delhi, and if you can picture a Google map of New Delhi in your mind, and various areas of that Google map would be coloured or encoded in various colours. Maybe the area around the embassies was coloured green, because there is a very low chance of fire within an embassy, given the fire safety that they have in place. Maybe the area around the airport was coloured red, because we've got planes going in and out all the time, and therefore there is a high likelihood of fire within the airport. So we could kind of run lots of calculations, and we could produce that map, and we could print it off, and we could give it to people, and there we have a fire risk model. It's static, it doesn't change. If we start and bring in other data sources, those data sources are real time, then we can start and create a model which will change and adapt. So in a kind of simple example, the chance of a fire during the rainy season is much lower than the chance of a fire during the summer. The chance of a fire occurring or the chance of an incident occurring on Independence Day, when everybody's out on the street, is much higher than the chance of an incident occurring at 12 midnight on a Sunday, when everybody's at home in bed. So you can start and bring in data in real time. Maybe you're bringing in weather data from various weather stations around the city. Maybe you're bringing in information from traffic cameras, from traffic signals around the city. And maybe you're bringing in information from Facebook and Twitter about what events are happening. And all of a sudden you can start and maybe not predict. Well, maybe you can predict if you've got enough data. We've got 13 years worth of data, so we can quite confidently say that in this particular area of Sheffield, at this particular time, on this particular day, there is a 90% chance that there will be an incident. In the UK, the ambulance service has already done this. So the ambulance service now have a predictive model where, and as you travel around the UK, you will see ambulances parked on the side of the road. And it's not because they've got nowhere else to go, it's because the ambulance service have done predictive analysis and are able to say that in this particular area, within this particular time frame, maybe an hour's time frame, there is a 90% chance of there being an incident which will require an ambulance. Therefore, at that particular time, we will put an ambulance in that particular area. So speeding up the response. Are there any open source API for R which is more user-friendly GUI to use for analysis? Sachin, yeah, yes there are. Yes there are. There are GUIs for R which make the process a little bit easier. I'm a C# coder by background, so I'm quite okay with the API, really. But yes, there are GUIs. What is the tool that was shown up for commercial applications? Is it a spreadsheet? Also, any other graphical tools for showing patterns? No, the tool that I've used, or the tool that we use to do all of this analysis, is the R package. It is the R software. Sorry, it had the TrainMine R package. If you dive into the presentation, and I know that the presentation will be available, if you dive into the presentation and look at the software slide, there's a link to the TrainMine R website, and from there you can get hold of the TrainMine R package, you can get hold of the R GUI. They're all open source, they're all free to use, and there are plenty of kind of instructions and papers, academic papers on the internet that will walk you through doing this kind of analysis, and that with the software being open source, it's free, and that a lot of the kind of resources on how to use the software and how to perform the analysis are also free. So you can start and leverage commercial benefit, and that is one of the reasons why I showed this particular software. So yes, I am an SAP mentor. Yes, I do teach SAP software, but I took the decision to demonstrate TrainMine R because it's open source, it's free, and you guys can get hold of it and have a play. Do I have any examples of real-time usage of outcome from such analysis? Marlin. Marlin, not yet. Real-time is not something that we've done yet. It's where we're aiming to. What we will do is we will take the model that we've created. We will take this R code that we are using to do this analysis, and eventually we will move across and we will start and use SAP software. SAP have real-time analytics software called HANA, and we will start and use their software and plug in these various data feeds from traffic analysis and weather. But we want to be in a position where we can give the fire service a lot of analysis and a lot of value before we start and move across and start using commercial packages. The insights that we're gaining already are going to change the way that the fire service deliver their service. They're going to change the way that the fire service stock or staff their appliances, staff their call centers, train their staff, and they're big changes for that particular organization. So really giving them a predictive fire risk model straight off the bat is something that this particular organization is really not ready for. So there is a degree of business thinking, and maybe I'm stating the obvious. I would encourage you all to remember there is a business, whether it's a fire service, whether it's a supermarket, whether it's a corner shop, there is a business behind this. And as geeky as we all are, as much as we love to kind of analyze this data and produce this code and produce this kind of insight, there is a business at the end of it, and that business has to take on board the insight that we give it and get value out of it. And some businesses are just not ready for the more advanced kind of insights, and it's a matter of working with the business to get them there in a stepwise fashion. So yeah, we'll do the analysis, we'll use this open source software, we'll bring out some really kind of nice insights. We've already done that in terms of clustering incidents and ranking incidents and looking at staff use and things like that, and we will steadily move them towards a kind of real-time position. Swayam, do you have any research topics on big data? We have loads of research topics on big data. We have research topics on big data with regards to healthcare. We've got some work going with Sheffield Council and the NHS, looking at older people and loneliness. We've got work with some government agencies looking more at security and how you can tell if a user is an authorized user based on their behavior by mining their behavior. We've got European research projects which are looking at the use of Twitter within security and Twitter with regards to extremists and things like this, terrorists. We've got research projects looking at Facebook data and social media data to identify organized crime. So in terms of research projects on big data, we've got quite a few, and that's there before we even start and kind of list the ones that our commercial partners are interested in. The university's got good links with industry, and industry is now starting to take an interest in what we're doing in big data, and just kind of getting comfortable with the idea of giving us lots of data. So for a company to release their sales data to a university is quite a big step for that company. You must understand that the sales data is commercially sensitive, and yet the insight that they could gain from looking at it is astronomical. So companies are just starting to come to terms or get used to the idea that universities might be able to examine this data for them and come up with some very useful insight. And why get the universities to do it? Well, we get access to hardware and software far cheaper than companies do, and we've got more time to analyze this data. So as a university, we're full of big data geeks. We've got big data PhD students and big data students who are quite happy to spend their time analyzing this data, gaining insight, and learning as they go, something which a company wouldn't necessarily do. As per my knowledge, R is a statistical tool. I would like to know how we can integrate it with big data tools. Sushit. It is a statistical tool, and I would say that I'm curious as to what you mean, in the sense that I would say that statistical tools are big data tools. We teach a lot of SAS, SAS, and that is a big data tool. It's a statistics tool. It's used by insurance companies, it's used by finance companies to model risks, to model financial models and insurance models and things like that. So that is one and the same. It's a statistical tool and a big data tool. Can we implement TrayMineR in MapReduce? Mahana, I honestly don't know. My question, if I threw it back to you, would be, can you implement R in MapReduce? If you could implement R in MapReduce, I don't see why you could not get the TrayMineR package and load that into MapReduce. The TrayMineR package is open source, it is freely available, and it is available in various formats. I know it's available in the Linux format, so in that sense, you may very well be able to. We do a lot of correlation-based analysis, but causality is not considered in correlation between attributes. How Google for prediction how to speak when trying to find correct relationships between different factors. I'm not quite sure what you're meaning by that particular question. I'm a geek by trade, not a statistician, so perhaps I could pass that question on to some of my statistical colleagues and kind of come back to you with an answer. If you want to drop me, Vibhav, if you would like to drop me that question in an email, my email address is kind of on the slides. If you'd like to drop me that question in an email, I'll quite happily ask some of our statistical geeks and see what kind of answer they can come up with, and pass that back to you. I'd be very happy to do that. Okay. That seems to be about it for the questions, ladies and gentlemen.
Well, thank you so much, Steve, for answering all the questions of our attendees. I'm really thankful to you for conducting this great session.
Thank you.
I would also like to thank all our participants for their support in making this webinar a success. The recording of this webinar would be available on techgig.com by tomorrow. Thank you all. Have a great evening.
Thank you, guys. Enjoy your evening.